Okay, sorry about that. We're just checking some things here. All right. So I'm thinking everybody is getting in, I hope. Okay, so we will get started here on lecturing on chapter 1. And again, it is sort of a little bit of introduction to sort of what chemistry is, scientific method, and things of that nature. And let us go here. All right, get that out of the way. All right, so obviously chemistry affects pretty much all aspects of our life, you know, from obviously medicine to things like the environment, the atmosphere, to things like food and cosmetics and all those type of things. We do sort of have chemistry that comes, you know, about at all times. Forensic science, right? Sort of CSI type stuff, you know. Obviously, all that stuff involves chemistry and so forth. Now, when we talk about chemistry, you know, what are we sort of really dealing with? What is, you know, sort of the main idea of chemistry? And really, for the most part, chemistry really does all pretty much revolve around the idea of matter. You know, pretty much matter is really important. Obviously, in chemistry, matter pretty much. If I get my thing here to write, there we go. Matter is pretty much anything that has mass and occupy space, which is, you know, pretty much everything right here. And when we think about matter, we oftentimes in chemistry really do study sort of how matter changes. And some common things that we look at is, you know, how matter changes, for example, as it goes for different phases. It goes from solid, say, to liquid to gas. We also study, you know, how matter reacts or how it resists reactions. And we study really the composition and structure and property, basically, of matter and how things basically do react here. So let's talk a little bit about, you know, chemistry. It's made up of composition, its structure, its properties. But as I mentioned before, really the heart of it is matter. And when we talk about matter, you know, there's really sort of 3 states of matter that we very often come across here in chemistry. And the 3 states of matter are solid, which is oftentimes abbreviated with an S, liquid, which is abbreviated with an L, and gas. These are really the sort of 3 states of matter. A lot of what we deal with is, you know, what happens as things sort of transition from one state to the next. So for example, you know, if we talk about sort of the solid matter here, when things are in their solid state, let me do my award-winning drawing here. There we go. Pretty much everybody is, you know, packed in there fairly tight to one another in the solid state. That's why when we think about things that are solid, you know, they're usually described as being rigid. They're hard to change the shape of it and everything. And that's really because, you know, pretty much they're packed in there tight to one another in most cases. They actually don't have enough energy to really pass one another in the solid state. And that's really why in the solid state, you know, they just kind of like lock in basically because, you know, they don't have enough movement to get past one another. So they just kind of lock in there. And again, that's why solids obviously are fairly rigid. When we get into the liquid state, things are still pretty much packed in tight to each other, but there is definitely a little bit more room for movement in the liquid state. And that's why when we think about sort of a liquid, right, liquids are fluid. And that's really because in the liquid state, they actually do have enough energy to sort of pass one another. And that's what, obviously what makes sort of a liquid a fluid sort of substance. Now, the last state of matter is the gas state. And in the gas state, we basically have everybody really completely flying around. They've completely separated from one another. They're flying around the container. And when you think about gases, and we'll talk about gases in a later chapter, when we think about gases, we think about pressure. And pressure basically results from, as they are flying around, they obviously have a good amount of energy. They're basically going to be hitting like the walls of the container. There's going to be a lot of collisions, and that's basically what's going to cause sort of the pressure. So a lot of what we deal with, in terms of chemistry is, as substances sort of transition from one state to the next, what's sort of happening. When we look at these things as we transition from one state to the next, they actually do have sort of specific names that basically are what we consider happening. So for example, if we take something that's in the solid state and we want to transition it into the liquid state, that pretty much is the process known as melting, right? Like if you took a, ice cube out, right? If you took an ice cube out, it's going to start to melt. Good news is, right, if your ice cube starts to melt and you feel really bad about that and you kind of want it back into its solid state, you could throw it back in the freezer, right? And it will freeze. So kind of going the opposite way, going from liquid back to solid, that is the process of freezing that's occurring. Now, if we take some liquid water and, we're maybe cooking dinner, some pasta or something like that, we put it on the cooktop there and we start to heat it up, the liquid water will start to basically evaporate and we start to see steam coming out from the liquid water. And that's the process where we go from liquid to gas. That's the process of evaporation, or sometimes referred to as vaporization. Now, when we take a gas molecules and we take it back to liquid, that is the process known as condensation. Any questions on that so far? By the way, feel free, again, if you do have questions, feel free to send me a chat. Feel free, if you like, unmute yourself and ask the question, whatever you'd like to do. Feel free, if you do have questions, feel free to ask them, obviously. Now, there's some other processes that we come across here in chemistry as well, as we go from solid directly to gas, skipping the liquid state altogether. And that's the process known as sublimation. You may be familiar with that. That's like dry ice. So if you ever seen dry ice, use dry ice, I guess, it starts out solid and then pretty much off it goes into the gas phase. There's no liquid mess or anything like that. As you may know or may not know, dry ice is actually not water. It's actually carbon dioxide. But that's a very common sort of example of sublimation that occurs. We could also actually go the opposite way as well. If we have a gas molecule, we could skip the liquid and actually bring it back to the solid state. And that is what is known as deposition, like you're kind of depositing something on it. I assume most of you are old enough to still remember CDs and DVDs before we stream things. They're really shiny, and that's sort of how they get it very shiny. They actually go through a process of deposition, deposit some metals on top of that, and makes those guys really shiny. So these are really what we sort of call changes of state when matter kind of goes from solid to liquid to gas. These are the different processes that occur. And these are some really important things that we, kind of discuss here in chemistry. And another sort of aspect of it that we discuss as well is energy. Energy is a really big part of chemistry that we sort of discuss. And there's really energy related to what we're talking about here. For example, if we are going through the process of solid to liquid to gas, if we're thinking about energy, you may be thinking, do I need to put energy in to do that? Do I need to put energy out to do that? And the answer is you actually do need to put heat and energy in as you do that, or it needs to be absorbed. So if you take these kind of simple example that we talked about there at the beginning, which is just an ice cube. If you take an ice cube out, it's actually picking up all kinds of heat and energy just from the surrounding air. Basically, it's picking up all that energy, and thus it starts to melt. If you take liquid water and you put it on the cooktop, you probably light a fire under it to boil it to make some pasta. You're obviously giving that water a bunch of energy, which is why it will eventually start to boil, which is basically the process of evaporation happening out the top there, where you see all the steam and stuff that's coming out. And when we do that in terms of energy, wherever my thing just went, there it is. When we take heat or energy and it's being absorbed or kind of put in, if you will, those type of processes are what are referred to as being an endothermic process. So somebody says, hey, this is a endothermic process. Basically what they're talking about is in terms of energy and heat, it is being absorbed by something or someone, I guess you could put it. The opposite is true if you kind of think about going in the opposite direction there. If we go from gas, or starting with gas, back to liquid, back to solid, think about just gas molecules. They're flying around, which means they really do have a lot of energy. So as they're flying around, they got all this energy. If we remove energy from the gas molecules, they're going to be flying around a lot slower. In addition to that, when they come in contact with other slower moving gas molecules, they're basically not going to have enough energy basically to escape each other. They're going to kind of lock in and kind of fall out of the gas phase and back into the liquid phase. And then in the liquid phase, if you continue to take out that energy, they're just going to really kind of lock themselves in and be in that solid phase. So as we kind of do the opposite process in terms of energy, going from gas to liquid to solid, energy is being released. And those type of processes, as we talk about here in chemistry, are processes which are referred to as being exothermic. Any questions on that there? And by the way, we will go over some of this stuff, obviously, a little bit more in some of these chapters. But, you know, these are basic things that in chemistry we sort of deal with. Energy, we deal with things changing states. We obviously deal with things that are reacting. Since we sort of have this little chart up here, let's talk about two other things that are sort of important to keep in mind. Now, when we talk about melting and freezing, for example, do these processes occur at the same temperature, or do they occur at different temperatures? So take a second and think what you think the answer is. And the answer is both of those processes occur at the same temperature. And you may be saying to yourself, how can that be? One is freezing, one is melting. How could they occur at the same temperature? So for example, let's take water, for example. Water freezes and melts at 0 degrees Celsius. At exactly 0 degrees Celsius, when you're talking about water specifically, you actually have both phases there at the same time. And what I mean by that is you have solid phase and you have the liquid phase happening at the same time. Sometimes people refer to it as like ice crystals, got a little bit of ice, got a little bit of liquid water happening, and it happens exactly at 0 degrees Celsius. You have both of those guys basically happening at the same time. Now, if you get a little bit above 0 degrees Celsius, you will transition into liquid water. It's not really until you get a little below 0 degrees Celsius that you truly transition into ice or solid at that point. But exactly 0 degrees Celsius, these actually occur at the same temperature. The only difference is if you decide to continue heating it, it will start to go in this process and go from solid to liquid, obviously to gas. If at 0 degrees Celsius, you just see continue to take out energy, it will go basically in this process and go to solid. Same thing occurs here when we talk about evaporation and condensation, also occurs at the same temperature. And since we use water, which is a super common example, for water, that is 100 degrees Celsius, basically where that occurs. Same sort of thing happens at exactly 100 degrees Celsius. You basically got both phases there together. So you got some steam, you got some liquid happening. In fact, you don't usually notice it, but at the surface really of any liquid, you got a constant stream of guys going out of the liquid into the gas phase and back into the liquid phase, kind of back and forth. Although we can't visually sometimes see that happening, there's a constant at the surface of a liquid, that process occurring. In terms of energy, again, it takes a lot more energy to actually do this transition here, going from liquid to gas or gas to liquid, than it does to do this transition. And that's because when you think about things that are solid, they're pretty much packed tight to one another. And when you go into the liquid phase, they're still relatively close to one another. But when you go from the liquid phase to the gas phase, you are completely breaking everybody apart. It takes a lot more energy to do that transition. Just to give you an idea, and again, you don't really need to know these numbers or anything like that, to do the transition for something like water, for example, to go from solid to liquid or liquid back to solid, it takes about 333 joules per gram. Not really important. Joules is a unit of energy, but per gram of water. To do the transition to go from like liquid to gas or gas back to liquid, it takes something like 2,260 joules per gram. So if you just look at the numbers, you can see it takes an incredibly amount more energy to do that transition as we go from liquid to gas, again, because in that transition, we're pretty much breaking everybody apart. And again, you don't need to know those numbers or anything like that, just an example of it. Lastly, here on this, just for reference point, this is usually what we refer to as the normal melting point. And over here, this is usually what we call the normal boiling point. And for water, that would be 100 degrees Celsius and 0 degrees Celsius for water. And if we are not talking about water, then these temperatures would most likely be different if we're talking about a different substance. So the 0 degrees Celsius, the 100 degrees Celsius really is specific for water. Any questions on that there? So as we sort of talked about a little bit earlier here, again, matter is basically anything that occupies space and pretty much has mass. It's pretty much everything along the way. Things like antacid tablets, water is H2O, right? Antacid tablets are solids, right? Water, most of the time is liquid. Oxygen, by the way, is, when we talk about oxygen by itself, it is really O2. Is the formula there for oxygen. Oxygen actually comes as what is sometimes referred to as a diatomic molecule, which is a fancy way of saying there are two oxygen atoms in that particular compound. It's what's referred to as a diatomic molecule. And carbon dioxide, which is what we exhale, again, as a gas. So, matter obviously comes in all those different states as we just talked about. And sometimes oxygen, hydrogen is another example of something that's diatomic, for example. There are certain elements that how they come is they basically come as, kind of two things together. Some don't come that way, but others really do come that way in terms of elements. And we'll talk about sort of the difference of what those guys are as well. Chemicals, obviously chemicals are found in all kinds of substances. And as we talked about, there's a lot of sort of chemistry that goes into things that maybe, again, you may not think of, chemistry being involved in. Things obviously like toothpaste there, things like food as well, food chemistry. You know, how they get those things like candles, right? To smell like whatever they smell like when it's candle day over there at Bath and Body Works or whatever that store is there. You know, all those candles that smell like something different. You know, that all involves chemistry and stuff like that. Here are some commonly found chemicals, you know, in some of the stuff that we use a lot. And again, so it really does sort of go over a lot of different areas. So which of the following things contain chemicals? Sunlight, fruit, milk, breakfast cereal. So if we take a look at these things like fruit, things like milk and breakfast cereal, I would think probably does contain some type of chemicals. Sunlight really doesn't contain any chemicals. It does give off heat and energy and stuff like that, but not really made up of any particular chemicals or anything like that. So let's talk a little bit about sort of elements, molecules, and compounds. And, you know, sometimes people get those three sort of words sort of mixed up or what they mean. When we talk about something, for example, since I just sort of put it out there a second ago, you know, we talked something about elements, right? Elements are your basic units of matter. They're basically made up of atoms, and atoms basically contain protons, neutrons, and electrons. All right. Now, when we put atoms together, we get a basic definition of what is referred to as a molecule. And a molecule is a basic definition that means you put two or more atoms together. Now, another word that sometimes confuses people as we go through it, and we may see this a little bit later on here in the chapter as well, is a compound. A compound is made up of two or more elements that are together, or two or more atoms of different elements. So, for example, there are certain elements, if you look on the periodic table, that come as molecules. So hydrogen's an example of that, oxygen's an example of that, iodine is an example of that, chlorine, fluorine, bromine. I feel like I'm missing one there. Nitrogen, I think. There we go. These are all elements, just like everything else that you would see on a periodic table. And they come again, as I mentioned just a second ago, as was referred to as a diatomic molecule. And that again just basically means, as I drew a second ago, that when we talk about hydrogen, it basically comes as two together. So two of them are bound together. That's naturally how they come. So if somebody says, hey, I have hydrogen by itself, elemental hydrogen, or is usually referred to as molecular hydrogen, what they're basically saying is it would come as two hydrogen atoms bound together. So you will never have molecular hydrogen coming as like a single atom by itself. It's just not how that particular element comes. All these guys, again, come as twos. Pretty much everybody else on the periodic table in terms of an element comes as a monoatomic element. So if you had, say, a piece of iron metal, which is Fe is iron, it basically comes as one iron atom together by itself. No other combination there happening. So iron, all these guys here, they are all elements. These guys here, the hydrogen, the oxygen, the iodine, the chlorine, the fluorine, they are also molecules because they meet the definition of we put two atoms or more atoms together. They happen to be the same atoms, and that's okay. And another common example, for example, is something like water. Water is basically, if we kind of draw it, looks something like this. I'll put circles around him. Water is basically made up of hydrogen atoms and oxygen atoms. Water is not an element because an element needs to be the exact same element. Basically, it can only be made up of the same element. Water is a molecule because it is two or more atoms that are together. Happens to be different atoms, doesn't matter, it's still a molecule. Water is also a compound because it is two or more atoms of different elements together. So these two words sometimes confuse people in terms of, what is the difference between a molecule or a compound? So the basic definition is a molecule is just simply two or more atoms together. They could be two or more atoms of the same element. They could be two or more atoms of different elements, while a compound has to be two or more atoms of different elements together. So to sort of wrap this up, and we may see it again a little bit later here, if we look at hydrogen, H2, this is an element because it only contains hydrogen atoms. It is also a molecule because it is two hydrogen atoms together, but hydrogen is not a compound because it, again, is only made up of the same element. Water is a compound because it is made up of two or more atoms of different elements. Water is also a molecule because it's made up of simply two or more atoms. Water is not an element because it is made up of two different elements. Any questions on sort of the differences between those guys? Take a special note here to do that because, again, sometimes people get very sort of confused on those things. Any questions on that? Okay. So element, also a molecule, not a compound. Whoa. And this guy is a molecule and can be a compound again, but no element for that particular guy. All right, so let's talk a little bit more here as we're sort of introducing some of these topics. And again, we will go back and cover some of these topics as we continue through this chapter and obviously other chapters as well. But, a very big part of science and especially chemistry is the scientific method. And the scientific method really involves several steps, but really the scientific method all really begins with an observation. Really an observation is the thing that basically sort of kicks it off. So maybe you're looking for something, maybe you just happen upon an observation and go, that seems kind of interesting. And when we make an observation or sort of see and observe something, a lot of times in science and chemistry, what we try to do is come up with a possible explanation as to why maybe we are observing what we are seeing. Usually that is what is referred to as a hypothesis. A hypothesis is usually a pretty good one, is a testable, like you're able to do some type of experiment, you're able to kind of put it to a test, explanation of, what you observe. So we make this sort of observation, we make this hypothesis, then we go and test the hypothesis through experiments. Now, I will say in most cases, what ends up happening is, it can turn into, depending, I guess, on your perspective, or if you're the one doing the experiments, perhaps a vicious circle, because typically speaking, when you do experiments, you then start to observe some other stuff happening. And then you tell your boss and they go, cool, why don't you do some more tests? All right. And you come up with some more hypotheses and more experiments. And it can perhaps kind of rove into a hopefully never ending cycle, but hopefully it ends at some point. But ultimately what sort of ends up happening is we usually will end up at some point with one of two things. Either a theory is sort of developed through sort of this method, or what is sometimes referred to as a law. And there is sort of a difference between those two things. And here's sort of a flow chart of it. And again, sort of the difference between sort of a law and a theory or a conclusion is a theory for the most part is maybe proven down the road not to be necessarily correct in all aspects. It could be revised and so forth. So for example, there is what is known as Dalton's atomic theory. And Dalton's atomic theory, there's several parts to that theory. And it was later found that although there's several parts to that theory, there are a couple parts that really are sort of incorrect. And it was found later on that, not all of it is correct. Some of it is still correct. Other parts of it is not. There's something known as the Bohr's model or theory of the hydrogen atom, which is a very nice theory. It works perfectly for the element hydrogen, which has only one electron. But then you start putting more electrons like everybody else, it doesn't really hold up. So when we talk about a theory, it's I won't put a tentative explanation of what's happening, but it's sort of an idea of what you observe, why you're observing it, but it's not necessarily set in stone is one way to sort of look at it. It can be sort of modified. It can be perhaps later found to not be sort of correct as well. And that's different than a law. A law is basically kind of like set in stone, like always occurs that way, no matter sort of what the situation is. So for example, we have what is referred to as the conservation of mass, which basically means in a chemical reaction, we really don't lose anything along the way. And what that means, for example, is if you started a reaction with, say, 4 carbon atoms, those 4 carbon atoms have a certain mass. And when the reaction's over, those 4 carbon atoms will still be there. It may be in a different sort of compound, may have moved around somewhere else. But because we started with 4 carbon atoms and we ended with 4 carbon atoms, the mass of those 4 carbon atoms is basically conserved. As we'll talk about when we get to the sort of balancing reactions, that's really the basis of balancing a chemical reaction. Whatever we start with, we don't lose. We always end up with it at the end. Any questions on that there? So, when we think about observations, we think about experiments you could do and so forth. For example, here's one I think the book has. Yesterday, you went to go visit your friend. Soon after you arrive, your eyes started to itch and so forth. So you observed the cat. You could come up with a hypothesis of perhaps you are allergic to cats. You could test that by, obviously, if you leave your friend's home, if the itching and sneezing stops, perhaps you were correct. If the itching and sneezing did not stop, then maybe you're not allergic to the cat, right? And maybe you just have a cold or something like that. So, these are what we do, perhaps when we make some observations. An observation upon leaving your friend's home, again, the itching and sneezing, did stop. The observation would support your original hypothesis that you were allergic to cats. So again, the idea of a hypothesis is really something that is sort of testable, something that you could test and do some type of experimentation. Experiment 2, visiting the second friend with a cat causes your eyes to itch and begin to sneeze further. That obviously would indicate that perhaps you should stop visiting friends that have cats, I would imagine, in that particular case, right? Any questions on that, right? All right, so let's identify each of these as an observation, a hypothesis of an experiment, or a conclusion. So take a second and think about what you think these are. Okay, let's take a look here. During a visit to your gym, your trainer records that you ran 25 minutes on a treadmill. That is clearly an observation, right? He observed you doing that. Scientific studies show that exercising lowers blood pressure. That is sort of an outcome, obviously, of experiments and so forth. So that would be like a conclusion or a theory or a law, I guess. Your doctor thinks that your weight loss is due to an increase in exercise. That would be a hypothesis, right? It's sort of a tentative explanation of what is going on. Any questions on any of those three there? So let's take a look at some of these here. Again, same idea here. We're looking at, is it an observation? Is it an experiment or a theory? So let's talk a little bit about this. A blender does not work when it is plugged in. That is a observation, right? Probably a sad one because you probably plugged the blender in to do something with it. So obviously you observed it did not work. The blender motor is broken. Well, and I guess unless you are a blender repair person, that is probably a hypothesis. Probably the repair person would make the same type of hypothesis, perhaps. The plug has malfunctioned. Again, maybe it's the motor, maybe it's the plug. So that would also be a hypothesis. The blender does not work when plugged into a different outlet. So that would be a experiment that you did. Why would you do that? Well, you want to make sure that perhaps the plug that you're plugging it into actually works, right? So that would be an experiment. The blender needs repair. That would obviously be a theory in that particular case. Any questions on that there? All right, so let's talk a little bit about some math skills. And again, sort of this a little bit of an introduction before we get into some of the, I want to say real stuff or about the actual calculation and stuff. But, math is really important in chemistry. Being able to properly sort of rearrange equations and stuff like that is a really important skill. If that is something that is difficult for you, you should try to take some time and, just make sure you practice some of that. So that doesn't hinder your process of sort of doing a lot of the problems. I will say, and maybe I did last time, or maybe I didn't, we talked about that this class basically covers general chemistry, organic chemistry, and sort of biological chemistry. Pretty much the very front part of the class is math heavy, if you will. There's a lot of calculations and stuff like that, all the way through, I want to say maybe chapter 9-ish, isn't that right? 1 through 9. It's all the general chemistry stuff. It really does relate to math and solving problems and stuff like that. So if you're okay with math, you might enjoy that part. Even if you're not okay with math, you might enjoy that part. When we get to organic chemistry, the good news is you don't even need to pick up a calculator. There's really no calculations that will happen in those chapters, which is like, I think 10-ish or 11 on. It's a little bit more of, I will say, memorization and those type of things as well. So you could kind of think of this class sort of in two parts. First part's kind of math heavy, if you will. Second part is a little bit pretty much no math and more memorization, stuff like that, just to kind of give you an idea. Obviously, some numbers we want to make sure we understand places and stuff like that. The 2 is the thousands place in this case, hundreds, tens, and ones place as we come through here. 6.407, 6 would be the ones place, and this is the tenths place, right? Hundredths and thousands place when we talk about decimals. Basically 0.1, 0.01, 0.001. So basically tenths place, hundredth place, and thousands place as you come through here. Now, if we look at this one here, 15.24, we have in this case the tens place, the ones place, the tenths place, and the hundredths place as we come this way through this number. Now, when we talk about numbers, it's really important, when you do calculations, and sometimes we'll do some of them here. But sometimes when we do calculations, especially with energy, although we don't do a ton of energy calculations in this class, sometimes we do get a number that's either positive or we do get a number that's either negative. And, sometimes people think, well, should I just make it all positive, the number, is it that important to keep the positive or the negative? And it actually is, sometimes the positive or negative is a really important aspect of a value that you get. So for example, in chemistry, when we talk about energy, which we just did not too long ago there, and we talked about kind of two ideas, an exothermic type process where heat and energy is given off, or an endothermic process where heat and energy is absorbed. When you do like an energy calculation, you typically will get a negative number for exothermic and a positive number for an endothermic process. So although you may think to yourself, positive and negative doesn't really matter, in the case of something like energy, for example, in chemistry, if you tell somebody, hey, the energy value was minus 250 joules, that would tell somebody just by the negative being there that what you just did was an exothermic process that released energy. And that would be different if you told somebody it was like a positive 250 joules of energy. That positive would tell somebody, obviously, that it is a endothermic process. Heat and energy is gained. So again, we don't do too much with the energy calculations in this class, but if you do get a negative number or a positive number, sometimes it really does have a meaning in chemistry, and it can give you some information that's, relatively important. Most of the time, though, when we do deal with positive numbers, obviously, we don't usually write the positive sign, but we definitely do write the negative sign, if you happen to come across a calculation that's negative. And a reminder that if we take a positive number and multiply it by a positive number, we get a positive number. We take a negative number and multiply it by a negative number, we get a positive number, right? And if we take a negative number multiplied by a positive number, we get a negative number. And again, just a reminder on that. By the way, on your calculator, in case you're not sure, you do have a positive negative button on most calculators, and it does look like this. One of those two buttons usually is actually a negative and positive button to make a number negative if you had to do some type of calculation with it. We're going to talk a lot about your calculator and how to properly use it. I'll spit that out, I think. And I'll be honest with you, it's what causes a lot of people problems is punching the stuff into their calculator. I've seen a lot of work that was set up correctly, and then you look at the answer and go, where did that sort of answer come from? And a lot of times people really do struggle with punching their stuff into their calculator. So a reminder, as I probably mentioned last time, that, make sure you do have your calculator with you during these lectures, obviously, and discussion. And make sure that you are really working these problems, punching these numbers into your calculators, and making sure that you are getting sort of the correct answer. Because I can't tell you, how often people really just mess up on punching it into their actual calculator. A couple examples here. Obviously, 3 times 2 is positive 6. Again, 2 negative numbers multiplied together will give us a positive 6. Here's our 1 positive, 1 negative number. Obviously does give us a negative value when it's all together and you multiply it. Dividing works the same way. If you divide 2 positive guys, you do get a 2. And if you divide 2 negative guys, you get a positive number as well. You divide a negative and a positive, you get a negative number as well. Let's talk a little bit about fractions, for example, here. When you work out a problem, and perhaps maybe you work out a problem, you end up with like an answer of 1/4. That is not the right way to give your answer. You should actually do the division and turn it into like 0.25. So please do not give your answers as fractions. Please actually do the multiplication or division of it and give it sort of decimal form number for it. Not so bad in this example, but I've had people literally write for answers 325 miles per 17.45 hours and circle it. That just makes me think you're like too lazy to actually divide those two numbers. So make sure that you do not leave things, especially in chemistry class here, as fractions. Make sure you take the extra step there and actually divide it, and make sure that you get a sort of a number with a decimal or whatever number you may get there. As I mentioned before, here again with our negative and positive, if we divide, we do end up with a negative number. Other common math things we do obviously is adding and subtracting. Here we just add. Again, we do not put the positive in there. If you add two negative numbers, you end up with a negative number. If you add a positive and a negative together, these two guys here basically turn this into, you're basically multiplying a positive and negative guy together, turns it into a negative, and you actually subtract. So 12 minus 15 leaves us a -3 when it's all said and done. Subtraction, right? Again, when you subtract, you're basically changing the sign because you're multiplying basically -1 times plus. So negative and positive turns that into a negative. So we'd actually be subtracting here. Negative and a negative are being multiplied together basically here, turning that into a positive. Again, same here, turns it into a positive and turns that into a negative as well. So hopefully most of these things are sort of review to you, but let us talk about, again, that root of most people's problems is our dreaded calculator here. So let's talk a little bit about certain things that we see on the calculator and, how to find really important buttons. First really important button is the one perhaps you're familiar with, scientific notation. We'll talk a little bit about it later. But basically scientific notation is a number like 1.25 times 10 to the 4. And I would probably imagine that most people sitting here, most people in class, although they have a calculator and maybe they even have a fancy calculator, not really sure how to actually use the calculator. So one button that we use a lot in this class is actually the exponent button. So on everybody's calculator, you should have an exponent button. That calculator button usually will look like an EE button. It may be an EXP button. And to be honest with you, if you have some of the newer calculators that are sort of being produced, it may even have a button that's like times 10 to the n or something like that. If you have this button, we'll talk about you in just a second. But if you have these two buttons, you pretty much can enter things without parentheses. So what I mean is if I was to enter this into my calculator, what I would put is 1.25. I would then hit my exponent button. And when you do that, typically on your calculator, it will go 1.25 and maybe pop a E there. It may go 1.25 and maybe pop up a couple of zeros. Maybe it'll say times 10 here. When you hit the exponent button, so when you hit any of those buttons, what that represents when you look at a number that's sort of in scientific notation is the times 10 part. So that's basically what these buttons represent. And what that means is when you're putting this into your calculator, you don't have to hit the multiplication button. You shouldn't hit what most people like to do, like I'm going to hit this button here and the log button, the inverse log. You shouldn't do that either. Basically, when you hit that button, that takes care of the times 10 part, which means all that is left really is a 4. You would hit 4. It would put a 4 here. It would probably turn this guy into a 4. And that would be the proper way to punch a number that's in scientific notation into your calculator. We definitely will see a lot of numbers in scientific notation in this class. You do need to be able to kind of push it in correctly on your calculator. This also goes for a number that perhaps is a negative exponent. So as we talked about just a second ago, for example, if we took 3.2 times 10 to the minus 4, you would approach it the same way. You would hit 3.2. Again, you would hit your exponent button. That takes care of this part of the number. But we do have a negative here, which means that you do need to then hit your negative button, which, as we talked about before, looks like that. Or again, it may look like this. Not your subtract button, which is a common mistake that people make. People think that this button here is my negative button. It is not, as you can actually see it right here on this particular calculator. That is the basically negative button, right, to change it. When you do that, it will put a negative here. It'll make a negative here. And then what you're left with is you would just put 4. It would do 4. And again, turn this guy into a 4. And now you would have properly put that into scientific notation. That exponent key is the thing that gives students a very hard time. And, you know, you could oftentimes figure out if you are sort of doing it correctly by your answer. So sometimes you'll get an answer and the front part of the answer looks really good, but the exponent part, it's off by like 1 or something like that. And that usually is how you're entering into your calculator when you do that. Any questions on that there? Now, I don't want to forget the people that actually do have this button over here. And we'll probably see some more examples later on in this chapter. But if you do have this button, because of the way the calculator is typically programmed, if you do contain that button, you essentially need to put parentheses around every number. And what I mean by that is, let's just take the 1.2 times 10 to the 5. If you have the button that I just circled here, you would actually have to start with opening a parentheses and then go 1.2 and then hit that button. And on your calculator, it will look like this, 1.2. It most likely will hit times 10. And then you'll have like a blinking cursor up there on top. Then you would put the exponent in, which is 5. You would hit 5. And then it would be 1.2 times 10 to the 5. And you may think, well, I'm done, right? But you will have this problem that your little cursor guy is blinking and is still on top, which means you need to actually bring it back down, which means most of the time these type of calculators also have like a little circle button in it. And that little circle button usually looks something like this. And what you would need to do is hit this side, and that will bring this down. And then you could actually close the parentheses. And you will end up with something that kind of looks like this. So if you do have that button, you know, there's nothing wrong with it, but you really do want to make sure you understand how to properly put that into your calculator so you do not sort of put it in incorrectly. And if you don't put the parentheses and you have that particular type of calculator, just based on the way it's programmed, it will do it wrong and it will do the wrong math. If you do have one of these guys in terms of your button, you don't need any parentheses. You can put as many numbers as you like by using those buttons. But if you definitely have the other one, you usually need to kind of put parentheses. I would say most of the time they're the models that are like maybe blue or green and they got like the white trim on the outside is usually the ones that have sort of that button on there. Any questions on our first calculator type of definitions here? And again, we will talk about how to punch these things in as we go through it and hopefully make sure that you properly sort of understand it. All right, so let's talk about calculator operations. Again, sometimes you do need to put parentheses as you do things. You want to make sure that you hit the right thing. But I'll be honest with you, the other very, very common mistake that people do is, for example, if they have a problem like, let's just take 325, and then we're going to times it by 25, and then times it by 12, And then we're going to divide those numbers by like 323 and like 42, right? So people go, okay, I'm just gonna lay all that up into my calculator. I'm gonna go 325 times, and we would be, by the way, multiplying the top, right? And then coming back and dividing by the bottom. So most of the time people go like 325 times 25 times 12, hit the divide button, 323, hit, and then multiply it by maybe 42 and get the answer and go, that is wrong, and not get the right answer. And that's because you do need to make sure you put parentheses as you're entering in multiple stuff. If you don't want to worry about the idea of having to put parentheses and that type of stuff, when you have a problem such as this, there's a very simple way to, it may not seem simple, but it's a really, I'll put it this way, maybe foolproof way to punch these numbers into your calculator without screwing up, basically. What it means is if you're going to multiply something there up on top, you pretty much could take as many numbers as you want and multiply them together. So for example, if I was punching this in the calculator, I go 325, I would hit my multiplication button, I would hit 25, hit my multiplication button, hit 12. And then at that point, that is everybody on the top. It's a good idea at that point to hit your equals button and get an actual number. Then we want to actually come back and divide by what's on the bottom. So instead of trying to put everybody on the bottom in at once, it's best to do them individually. I would then take my divide button and take 323. And you know what I'm going to do after that? I'm going to hit my equals button. And then that basically will divide it properly by 323. Then I will divide what I got now by 42 by doing the division. And we got there 42, and then hit equals. My suggestion is, again, if you have a situation like this where you need to divide something by a bunch of numbers on the bottom, hit that equal sign every time you do it. So kind of divide each number individually, and you usually will get the right answer. Again, I've seen many, many times people try to put it all in at once. And again, if you're not extremely careful with parentheses and making sure you do it correctly, you will get the wrong sort of answer. Any questions on that there? Now, sometimes we are given sort of information in percentages. And, you know, sometimes percentages are maybe not helpful in terms of doing a calculation. But when we think about percentages, oftentimes we can turn them into like a conversion factor. So for example, right, if you got 80% on your exam, right? So if you laid up a 80% on your exam, what does that really mean? Well, it means in most cases, if your exam was 100 points, you basically got 80 points out of 100 points, right? Which is why when you take 80 divided by 100, you get, and times it by 100, you get 80%. We can turn something into a usable sort of conversion factor when you have a percentage by usually assuming 100%. And what that does is pretty much not change the numbers. So if I had a 62% by mass sodium chloride solution, what does that really mean? Well, that really means that you have basically 62 grams of sodium chloride in 100 grams of solution, which you could use as like a conversion factor. Conversion factor is basically a fraction, right? You could also flip it around if you needed to. You could say up on top in 100 grams of solution, I would have 62 grams of sodium chloride. So a very kind of easy and convenient way of turning something from a percentage into sort of a usable unit when you have a percentage is just to assume 100 of something. You could assume as much as you want, but the numbers would change. So to keep the numbers the same, when we assume 100 or something, that basically gives us our proper sort of conversion factor. Any questions on that? And that's what we see on the bottom there. An aspirin tablet contains 325 milligrams of aspirin, and the tablet has a mass of 545 milligrams. What is the percentage of the aspirin in there? So in the tablet of aspirin, there's 325 milligrams of aspirin. The total mass of the other, everything together, is 545. Divided times it by 100 basically tells us that a tablet of aspirin in this example is basically made up of about 59.6% of the active ingredient that makes it an aspirin. Same thing here, you know, if we want to know the percentage of something, we would take our 5 red balls, for example, over our total number of balls, times it by 100, and that would tell us that, you know, in 100 sort of balls there, it is 5% red. And here we have 50 out of 100, which would be our total percentage of green balls, which would be 50%. Clearly our color choice here was green, right? We have 50% versus only 5%. That is red, which would mean there's something like 45% another color or multiple colors. Something that we do a lot is rearranging equations, and it's really important to be able to do that to solve for something specific. So in this basic sort of algebra type problem here, we have 2x plus 8 is equal to 14. This is kind of like the unknown of what we're looking for. So there's a very simple concept when you are rearranging equations or trying to solve for something. It's basically just a very simple idea of opposites. And what that means is when you have something like an equal sign and you want to move something from one side to the next, you kind of need to do like the opposite sort of process. And what I mean by that is if we wanted to move the 8 to the other side, we are adding 8, which means we would need to subtract 8 to both sides. And if we subtract 8 to both sides, we will end up with 2x, these guys will cancel, is equal to basically 14 minus 8, which gives us 6, right? Now, if we want to solve for x, if we look at this guy here where x is at, that is basically 2 times x. So the opposite of multiplying is dividing. So if we want to do that, we would divide both sides by 2. 2 divided by 2 is 1, which would give us an x. And 6 divided by 3 is 3 in this case. So whenever you sort of want to move something across an equal sign or to the opposite side, you basically do the opposite of what's happening to achieve that. Any questions on that there? Now, sometimes, you know, we're not given numbers, we're just giving some variables like P1, V1 equals P2, V2. This is actually a gas law. This is what's known as Boyle's law. We'll learn it later on. And Boyle's law we could solve for the first pressure, second pressure, first volume, second volume. Same idea here. Let's say we wanted to solve for P1. Right? So when we look at this, we are multiplying. So the opposite of it is dividing. So we would need to divide both sides by V1. And that gives us P1 is equal to P2, V2, V1. Another common gas law that we see along the way, P1, V1 over T1 is equal to P2, V2 over T2. As we'll learn in a later chapter, this is what is referred to as the combined gas law. Now, when you have some type of fraction like this on both sides, you could do the multiplying, you could do the dividing, but again, basically opposite location. So when we move something across an equal sign, it will end up in the opposite location. So let's just say that we wanted to solve for V2 in this case. And if we wanted to solve for V2 in this case, we need to move P2 to the other side, and we need to move T2 to the other side. When we look at P2 on the right-hand side, it is on top, which means when it crosses over, it will end up in the opposite location, which is on the bottom. When we look at the T2, it's on the bottom. When it goes across the equal sign, it will end up in the opposite location, and it will end up there on top. And that will give us the correctly rearranged equation. That is P1 V1 T2 divided by T1 P2. Again, I just basically move these guys to the opposite location, and that would equal V2 in this particular case. What we're doing when we kind of do that is we are essentially multiplying by T2 to both sides, which is why they cancel. And we're dividing by P2 to both sides, which is why they cancel. And that's how we end up over here. So kind of a quick way, easy way to rearrange is, again, if you have a fraction, you want to solve for some type of variable that's on one side versus the other, it will end up in the opposite location of where it started. Any questions on that there? Okay, then let us continue here. We're going to kind of skip graphs. We don't really do too much with graphs in here. Let's talk about some of the real stuff here in a little bit more detail. Let's first talk about scientific notation. So a lot of times in chemistry, we do come across really large numbers and really small numbers. So if you think about a really large number or a really small number, basically it's going to have a lot of zeros. So if you just kind of use the number like it is with all the zeros, the odds are you are going to probably lose a zero here or along the way. So for example, you know, if you had a number like 602.00000000000 and keep going. Clearly, if I try to use this number like this, I'm going to forget to write a zero somewhere along the way. Maybe I'll forget to punch it into my calculator correctly. Even if you had a really small number, like, you know, something like this, with a ton of zeros kind of happening there up in front, you know, nobody wants to kind of carry all those zeros around and try to figure out all that type of stuff. So when we have really large numbers, really small numbers, what we like to do is to write in scientific notation. Scientific notation has a general formula of n times 10 to the n. This first n is where most people really screw up and do not write proper scientific notation. This is a number between 1 and 10. So let's take a moment to think about what that means. That means that the number in front should not be 10, should not be 20, should not be 100, because that clearly is not a number between 1 and 10. It should not be a number that's like 0.2, 0.3, 0.4, because that is clearly not 1. It has to be a number between 1 and 10. The times 10 part to the little n, this could be a positive or negative number, and it really determines as to which way you need to move the decimal place to get yourself to a number between 1 and 10. So let's take a look at just like an example here. For example, if we have the, let's just say we had a number here, which is say 3225 or something like that. And 3225 doesn't have a decimal point written, but it's assumed to be here. So I want to get me a number that is between 1 and 10. If I move the decimal place to the left one spot, that now is 322.5. That clearly is not a number between 1 and 10. If I go one more decimal place, that is now 32.25, which again is not a number between 1 and 10. I go one more place. That is a number of 3.225. That is a number between 1 and 10. That is the correct way to start your scientific notation. I then would write times 10. The exponent up on top is how many places I moved it. I moved it 1 place, 2 places, and 3 places. It would be a positive 3 in this case. Typically, larger numbers have positive exponents. So obviously 3,225 is a relatively large number, greater than 1, has a positive exponent. Now, if you had a smaller number, like 0.003225, my decimal point is here. If I go 1 place, that is 0.03, which again is not a number between 1 and 10. If I go 1 more place, that is 0.3, which again, not a number between 1 and 10. If I go 1 more spot there, I guess I just ended up with the same number there. That will end up being 3.225, which again is a number between 1 and 10. Times 10 to the, I did move it 1, 2, and 3 places again, but this is a smaller number, which means it would get a negative exponent. So if you have to move the decimal place to the right, you get a negative exponent. As we see here, if you need to move that decimal place to the left, you end up with a positive exponent. Any questions on that there? These are some numbers with our scientific notation. Again, if I needed to turn this into kind of positional notation or a decimal form or a regular number, however you want to call it, I would start with the 1. And what does the 5 tell me? Well, it's a positive 5, which means it should be a large number. And I would then go 5 places this way and add some zeros, right? So 1, 2, 3, 4, and 5, right? So we go backwards, 1, 2, 3, 4, 5, and this would be turning that number into a regular number, if you will, as you go that way. This is a 8 times 10 to the negative 6. Again, the negative tells me it's a small number, which means originally my decimal place was over there on the left. I would start with the 8 and actually go the other way. 1, 2, 3, 4, 5, 6. Lay up some zeros there. And put my decimal. And just for notation purposes, typically in chemistry, we do put a 0 in front of the decimal. It keeps the numbers from running together. You clearly know kind of where this starts. But again, here kind of going the other way. 1, 2, 3, 4, 5, and 6. Any questions on how to go both ways there? Now, clearly, as we talked about just a second ago, this is where we definitely want to be using our exponent button if we're punching these things into our calculators, right? So make sure, again, that you are using the proper buttons to do that. All right. Sort of what we talked about there. Standard number, and again, in this case, moving at 1, 2, and 3 places, it gives us 2.4 times 10 to the 3. We will talk about why the zeros are gone here, and we'll talk about why the zeros are not here as well. But again, if we come this way, we get 8.6 times 10 to the minus 4. Here are, again, if somebody says, hey, this is like 10 to the 4, what that really means is it is 1 times 10 to the 4, which means if you need to put it into your calculator, you actually can put it into your calculator that way as well by taking 1, your exponent button, and 4, right, would be the way that you would put that into your calculator. Here's just some arrangements. We're really dividing here to get our negative exponents. Obviously, when we divide 1 divided by 10, we get 0.1. Again, needing to move that 1 place here, which is the negative 1. This guy needs to move 2 places, which is our negative 2, and so forth coming through here. All right, here's some measurements written both ways, and I'm sure you get the idea. And again, we'll talk about why some of these zeros were left off of the scientific notation as well. Just some other examples. And again, here's our exponent button, and making sure that we do properly put these things in to make sure that you do get the right answer. And again, you can see here, when you put it in, as I explained, you do not hit the multiplication button. You do not do any inverse log or anything weird like that. You simply just put that in with your exponent button. And again, it will display some of these sort of displays, depending on the type, obviously, a model that you have. Some calculators, you can actually put your calculator in scientific notation mode if you want every answer to be given to you in scientific notation. You may not want that, or you may want that. By the way, if you don't do that, obviously your calculator will just give it to you, most likely, in most cases, decimal form. Some cases they'll give it to you in scientific notation, but you don't have to do that. But again, that's just another way. So just to make sure everybody's sort of on the same page, so once you grab your calculator, why don't we just try a couple here, punch it into your calculator using your exponent button to make sure everybody gets sort of the same answer. Let's just randomly do 1.42 times 10 to the minus 4. And why don't we divide it by 3.2 times 10 to the 22. And why don't you do 3.11 times 10 to the minus 6. And let's multiply that by 4.6 times 10 to the 14. I'll do it as well. I just made it up. All right, so take your calculator out. Make sure you use your exponent button and see what you come up with. I'll do it as well. And we'll talk about it here in just a minute. Okay, let's take a look, since we're getting kind of to the end here of lecture. Let me grab my calculator. That probably will be helpful. So I'm going to write on the screen really how I'm going to punch it in. So again, on my calculator, just so you know, I have this button. I have the EE button. So that's why I'm going to write it. So you would want to type in 1.42. Again, you would want to hit your exponent button. And then it is a -4. So again, you want to make sure that you use your negative button there, whichever button you have, and then put 4. I then would hit the divide button and then type this guy in as 3.2. Again, exponent button. And this is a positive exponent, so I just need to hit 22 and an equal. Now that I wrote it, I'm going to actually do that. Let's see what we get here. 1.42. Exponent button, -4. Again, no multiplication button in there. Divided by 3.2, exponent button, 22. And on my calculator, we do get a number in scientific notation. And when we write what it looks like on my screen, and then we'll talk about a couple things that you want to make sure that you do. So on my screen, I get this number here. On your some other screen, you maybe will get something that looks maybe like 27, -27, maybe something like that, or just a badly written 27 up there. When you actually write your answer, if your calculator does give you the E and stuff like that, you do not want to write your answer with the E like that, even though it is what it stands for. You should then write your answer like 4.4375 times 10 to the minus 27. That would be the right way to give the answer. Remember that this EE button, or the E, basically represents the times 10 part. So when you are given an answer or writing an answer, you want to make sure you kind of convert it into proper scientific notation. Any questions on that calculation? Let's take a look at the last one here. Again, I'll write what I would type in. I would go 3.11. I would hit my exponent button. That's going to take care of this part of it. I'm I'm going to hit my negative button and 6. And then I'm going to hit my multiplication button. I'm going to go 4.6, hit my exponent button, which again will take care of this part, and 14 and an equal button. So if I do that, 3.11, exponent button, negative button, and 6 times 4.6, exponent button, and 14 gives me actually a big number here. So my calculator is not set to scientific notation. I end up with a number such as this. And if you wanted to, you could turn this into scientific notation by 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a long way to go. 1.4306 times 10 to the 9 would be turning that into scientific notation. Again, a couple of reminders that your calculator may not give it to you in scientific notation, may give you a big number like this. And again, when you give an answer, you may yourself want to turn it into scientific notation. Any questions on that? I will say, like I said before, if you do not know how to do this in terms of scientific notation or not sure on your calculator, make sure you see me virtually here. Maybe they're in discussion or something like that. Just, we could try to figure it out on your calculator, what buttons you need to push. One way usually, again, that you are maybe not entering it right is when you get an answer like what we got here, this part of the number is usually pretty good, but again, this part of the number is kind of off. And that's usually a pretty good signal that you have probably not entered it in correctly. Any questions on any of that stuff there? It's actually almost chapter 1 done, actually. All right. So we'll wrap it up for lecture.